Okay, in this opportunity we're going to discuss about the free energy in chemical reactions, and pretty much this is about how you can calculate free energy changes when you have a chemical reaction. There are some steps that are similar to other properties that we have discussed so far, for example the entropy and the enthalpy. So there are two types of calculation here that are going to be pretty much the same that you see there, but if you remember, free energy is going to be our measure of spontaneity. Okay, if the free energy for a chemical reaction is negative, then it's a spontaneous process. If it's positive, it is a non-spontaneous process. And if for whatever reason you obtain a free energy that is zero, then it's a system at equilibrium. So, three ways to calculate free energy changes in chemical reactions. Okay, so the first one I would call is the easiest one because it uses the free energies of formation of the substances participating in the reaction. And this is similar to what you have done before, particularly in 170, because this is going to be products minus reactants. So the enthalpies, not the enthalpies, the free energies of formation for the products minus the free energy of formation for the reactants. Okay. The restriction that this has is, of course, you're using free energies of formation, and usually they are tabulated for 25 degrees Celsius. Now, if you have reactions that are not at that temperature and you are away from that temperature, then you can still calculate the free energy for the particular reaction because you can use this equation. Back at the beginning of the chapter, we were discussing the spontaneity of a reaction is controlled by the enthalpy of the reaction and the entropy of the reaction, the changing enthalpy and the changing entropy for that matter. Okay? In this case, if you obtain, once again, if you obtain a negative value here, then the process is spontaneous. Okay? So, that uses a big assumption here, and that is that both the enthalpy, the changing enthalpy and the changing entropy are independent of the temperature. Is that actually true? Well, no, but since we want to simplify our life when doing these calculations, we are assuming that that is the case. Okay? Last but not least, we can also calculate the enthalpy for a reaction if you have a set of different reactions for which you know that information. And if you can obtain your reaction of interest out of those reactions, then you can calculate delta G for that particular reaction. This is also known as Hess's law. And you should have done something similar to this back in 170 using enthalpies of reaction. So just in this case, we're going to use free energy of reaction. So let's get started. So we are going to use free energies of formation in its products minus reactants. One thing to consider here, that this is very similar to what happens with the enthalpy of formation. The free energy of formation for pure elements is zero. Okay, so let's write that down. So enthalpy of formation, free energy of formation and enthalpy of formation for elements in their most stable form is equal to zero. Now the entropy of formation for elements, once again, in their most stable form is different from zero. Okay? And moreover, they are always positive. It doesn't really matter what the substance is. Could be an element, could be another compound. The entropies, the absolute entropies for any substance is always positive. So some of a table with some values for delta G of formation. The only thing here that is kind of important to notice is that elements, most stable form, the free energy of formation is zero. If you notice here this special case, carbon as a diamond is not the most stable form for carbon. Excuse me. Therefore, the enthalpy of formation for carbon in the form of diamond has a value different from 0 in the delta G of formation. Okay, and it could be positive values or negative values. It doesn't. It depends on the substance. Okay, but the possibility of having positive and negative values is open with free energies. For entropy is always positive values. So how do we use these free energies of formation? So we have this equation here. Okay, and we want to calculate delta G of reaction at 25 degrees, and we can perfectly use standard free energies of formation for this purpose. Okay, if we have our equation and we get those values, once again, remember that for oxygen is 0, then we can perfectly do this calculation. So our enthalpy of formation, not enthalpy, free energy. Our free energy of reaction is going to be, it's going to be products, right? So we have the enthalpy, the free energy of formation of CO2 plus 2 times the free energy of formation of water plus 4 times the free energy of formation of ozone. Okay, and yes, ozone is it's pure oxygen, but it's not the most stable form. That's why it's that value different from 0. Okay, so we have these are all the products, and then we subtract the reactants. In the reactants, we have the free energy of formation for methane, and minus 8 times the free energy of formation of oxygen. But since it's oxygen, this is 0, so we forget about it. Our free energy of reaction is going to be then, for CO2 is minus 394.4 plus 2 times minus 228.6, and I always suggest that you keep everything in parentheses so that you can keep better track of the signs. I mean, it's easier to keep track of the signs if you keep everything within parentheses, whether positive or negative. Plus 4 times 163, which is the free energy of formation of ozone, and then we subtract the free energy of formation of methane, which is minus 50.5. Okay, once you complete this calculation, you should obtain that the free energy of reaction for this particular case at 25 degrees is going to be equal to minus 148.3 kilojoules. Okay, so if we do this again, okay, if we use a different reaction, in this case now we have carbon monoxide plus nitrogen dioxide that goes to carbon dioxide and nitrogen, then what we need for this are the free energies of formation, which in the case of carbon monoxide is minus 137.2, for nitrogen monoxide is plus 87.6, for carbon dioxide is minus 394.4, and for nitrogen is 0. Why? Because it's an element and it's in its most stable form, therefore the free energy of formation is equal to 0. So our free energy of reaction is going to be then 2 times free energy of formation of CO2 minus 2 times free energy of formation of carbon monoxide minus 2 times free energy of formation of nitrogen monoxide. This is equal to 2 times minus 394.4 minus 2 times minus 137.2 minus 2 times plus 87.6. Okay, always keep everything in parentheses. The free energy of reaction in this case is going to be minus 689.6. Okay, for this matter, you need to have the proper values, the enthalpies of the free energies of formation, and then products minus reactants. Remember to multiply by the stoichiometric factor out of the reaction, and then you obtain the free energy for the reaction. Now, when to use that equation, delta G from enthalpy and entropy? Well, it depends on the data that you have. If you have data on free energy of formation, there is nothing to think about it. You use free energies of formation. If you don't have that, but you have the proper information, if you have the enthalpies of formation or the entropy of formation, then you can calculate everything. The ideal case is when I give you enthalpy of reaction and entropy of reaction. Then it's just plugging the numbers in the equation and you are set. But what if I don't give you those values, but I give you the enthalpies of formation and the entropies of formation? So what if I give you this? Well, you have enthalpies of formation, you have the entropy, the absolute entropy for each substance. Then you have to calculate, basically, step 1, you calculate, excuse me, the enthalpy of reaction. Step 2, you calculate the change in entropy for the reaction. And step 3, then you calculate the free energy of reaction. Okay? So in this particular case, the enthalpy of reaction is going to be enthalpy of formation of SO3 minus enthalpy of formation of SO2 minus 1/2 enthalpy of formation of oxygen, which is 0. Okay? Then this is going to be equal to minus 395.7 minus 296.3. And this is equal to minus 99.4 kilojoules. Okay, so that's step 1. That's the changing enthalpy for the reaction. Now for the entropy, it's going to be entropy of formation. Well, usually we don't refer to that as entropy of formation. That's just the entropy of the substance. So the entropy of SO3 minus the entropy of SO2 minus 1/2 the entropy of oxygen. Now, the entropy of oxygen is different from 0. We have a value for oxygen there, so we have to keep it. So this is going to be plus 256.8 minus plus 248.2 minus 1/2 205.2. And this is going to be equal to minus 94. Now notice that for entropy the units are joules per mole per Kelvin, so therefore these are 94 joules, not kilojoules. Okay, therefore we might need to convert these to joules per Kelvin is what we obtain here. So we have to convert these to kilojoules. Well, I mean, you can convert kilojoules to joules or joules to kilojoules, but you have to convert something to the proper units. Usually I would recommend convert everything to kilojoules because at the end, most likely you have to report your number in kilojoules. So this is equal to minus 0.094 joules per Kelvin. Okay, the temperature is 25 degrees, which is 298 Kelvin. Therefore, delta G of reaction, which is delta H of reaction minus T delta S of reaction, is going to be equal to minus 99.4 minus, let me keep the units, 99.4 kilojoules minus 298 Kelvin times minus 0.094 joules per Kelvin. Here Kelvin cancel with Kelvin, and sorry, this is kilojoules. This is kilojoules. And we end up with minus 71.4 kilojoules. This is the free energy for that reaction. Let's do one more. So here we have another reaction. It's pretty much very similar. Should have used a different one, but nonetheless. So let's say that we have the free energies of formation, and for NO, for nitrogen monoxide, now the delta G's, let's assume we have the delta H's of formation. For nitrogen monoxide is 91.3, for oxygen is 0, and for nitrogen dioxide is plus 33.2. Now the entropies for nitrogen monoxide is 210.8, for oxygen is 205.2, and for nitrogen monoxide is 240.1. Okay, so your enthalpy of reaction, it's going to be the enthalpy of NO2. Now let's just do it directly. So this is going to be 33.2 minus the enthalpy of nitrogen monoxide, which is plus 91.3, minus 1/2. Well, it's oxygen, right? It's 0. So this is nitrogen monoxide, sorry, nitrogen dioxide, and this is nitrogen monoxide. Okay, and what we obtain here is minus 58.1 kilojoules. Now the change in entropy for the reaction is going to be the entropy of NO2, which is 240.1, minus the entropy of nitrogen monoxide, which is 210.8, minus 1/2 the entropy of oxygen, which is 205.2. And this is minus 73.3 joules per Kelvin, which is the same as minus 0.0733 kilojoules per Kelvin. And here our delta G then is going to be the enthalpy minus 58.1 kilojoules minus the temperature is still 25 degrees, so it's 298 Kelvin, times minus 0.0733 joules Kelvin. Okay, and our result here is minus 36.3 kilojoules. That's the free energy of reaction for this particular reaction. You use enthalpy data, you use entropy data to calculate this with this equation, delta G equals delta H minus T delta S. Remember, the advantage of this equation is you can use different temperatures. Because if you are using delta G of formation, they are all set to, most of the time they are set to 25 degrees. So the delta G that you are calculating there is representative of the reaction if the reaction happens at 25 Celsius degrees. Now, delta G relationships. This, in other words, this is Hess's law. And basically, the concept behind this is that you have a reaction of interest for which you want to calculate the free energy of reaction, and you have several other reactions from which you can obtain that reaction of interest. Basically, you have to manipulate your set of reactions. You can multiply, you can divide, you can invert, and whatever you do to the reaction, well, you do to the enthalpy to the free energy of that reaction. For example, if you multiply a reaction by 2, then you multiply the delta G by 2. If you divide by 3, then you divide your free energy by 3. And the trickiest one is that if you invert the reaction, then you have to change the sign. Okay? So, but whatever you do to the reaction, then you do that to the free energy of reaction. And now, how we do that? So we have our reaction of interest, which is this one. Okay? And we have 3 reactions. And basically the protocol here is that you start looking for every single substance that you have in your reaction of interest. You try to locate them in your reaction, in your set of reactions. So it doesn't really matter which one you start with. So let's assume that we start with carbon here. We look at our reactions, and the only reaction that contains carbon as a solid is the second one. You need 3 moles of carbon as a reactant. This reaction is giving you only 1 mole of carbon as a reactant, so we have to multiply this by 3. Which means this enthalpy we have to multiply by 3. Okay? So if we rewrite this equation, then we have 3 carbons as a solid plus 3 oxygens as a gas. That goes to 3 CO2 as a gas. Okay? We move to the next one. The next one is hydrogen. And if you search your reactions, then hydrogen is here. Okay? That reaction gives you 2 hydrogens as a reactant, but you need 4 as a reactant. So this equation has to be multiplied by 2, which means we multiply the free energy by 2 in that case. Okay? So if we rewrite this equation, then we have, let's put this sign here, we have 4 hydrogens as a gas plus 2 oxygens as a gas, and you obtain 4 water molecules as a gas. Okay? Last but not least, we have C3H8 as a gas, as a product. Once you use one equation, then you kind of forget about it. You don't want to modify it anymore, any further. So C3H8 is here. You need 1 mole as a product. This equation is giving you 1 mole as a reactant. So pretty much what you have to do here is to invert. And if you invert it, then you have to change the sign of the delta G. Okay? And if we rewrite this equation, then we have, all we did was to invert, so whatever was in the product side now is in the reactant side. So we have 3 CO2s and 4 waters, and you obtain C3H8 as a gas plus 5 oxygens. Okay? The next step is to, of course, let's check that we are actually obtaining the reaction of interest. So, and in doing so, you look at your set of reactions after the modifications, and then you select what you need to keep. You need to keep 3 carbons as a reactant. You need to keep 4 hydrogens as a reactant, and you need to keep 1 mole of C3H8. Everything else has to go. Everything else has to cancel. Okay? So let's start taking a look here. So we have, oops, that doesn't look good. Now let's go a little milder here. So we have 3 CO2s here as a reactant, and we have 3 CO2s here as a product. So we can cancel them. We have 4 waters here as a reactant, and we have 4 waters here as a product. So we can cancel those. And we have 5 oxygens here, And we have 3 and 2, a total of 5 oxygens here. So we can cancel those out. Okay, and we obtain out of this, where you're keeping everything that you need in the amounts that you need. Once you have that, your delta G of reaction is going to be the sum of all of that. So it's going to be equal to plus 2074 plus 3 times minus 394.4 plus 2 times minus 471.1. And this is equal to minus 23.4 kilojoules. Okay? So the process is you have to locate everything that you need in that reaction, in your reaction of interest, in your set of reactions, and modify them, modifying those reactions accordingly to obtain what you need. Okay? Then you select what you need to keep, and then you have to verify that everything that is extra, everything that you need, that you don't need in your reaction of interest, has to go, has to be canceled. Okay? And it has to be the same substance in the same state and the same number of moles in order to completely eliminate it from your reaction of interest. Okay? Let's do one more. So, as I said before, we start looking for the substances. Doesn't matter in what order you go, but you try to locate them in your reactions of your set of reactions. So here we have the nitrogen monoxide, and it's here in the last reaction. You need 1 mole as a reactant. This reaction is giving you 2 moles as a reactant. So technically you have to you need to divide by 2, which means this enthalpy has to be divided by 2. So if we rewrite this, then we have N2O gas goes to N2 as a gas plus half a mole of oxygen. Remember, you are dividing by 2. Next step, we are looking for nitrogen dioxide. And the reaction that gives you nitrogen dioxide is this one. You need 1 mole as a as a reactant. This reaction is giving you 2 moles of nitrogen dioxide as a product. So we have to divide by 2 and we have to invert. Why? Because you need reactant and this reaction is giving you a product. So you have to invert that. So we have to change the sign of this and we have to divide by 2. If we rewrite this equation, then now we have NO2 gas in this side, and we have 1 mole of nitrogen monoxide plus half a mole of oxygen as a gas. Okay? Now, the next step, you have to be a little more careful because you are looking for nitrogen monoxide. And nitrogen monoxide is here, and it's also here. Okay, you have already used the first equation, so you are not touching that equation. Therefore, if that equation actually is giving you 1 mole of nitrogen monoxide, but you need 3. You need 3 moles of that one. So if you have 1 here, there is 1 here, there is 2 there. So basically, you do nothing to this reaction. So you keep it as it is. So we have nitrogen as a gas plus oxygen plus oxygen as a gas, and we obtain 2 moles of nitrogen monoxide. Okay, and that enthalpy stays as it is. You don't change it, you don't modify it. Okay, let's keep track of what we want to keep. So we want to keep the nitrogen monoxide, we want to keep the nitrogen monoxide, and we want to keep the nitrogen monoxide. Okay, there you have your 3 moles of nitrogen monoxide. Everything else has to go. So we have nitrogen here and nitrogen there, 1 mole each. We can say bye-bye. And here we have 1 mole of oxygen, and here we have half a mole of oxygen, so that adds to 1, so we can cancel them out. Okay, so we are good to continue. The delta G for this reaction is going to be 1/2 plus 71.2 plus 175.2 plus 1/2 minus 207.4, and this is equal to plus 107.1 kilojoules. Okay, so these are 3 ways in which you can calculate delta G's. Many of these calculations, or this type of calculation, should be familiar. I mean, Hess's law, you study that in thermochemistry. Free energy of formation is the same treatment that you give to the entropy of the substance. We already covered that type of calculation earlier in the chapter, and it's also the same that you do with enthalpies of formation. So this, I don't think that's going to give you too much trouble. Hess's law can be tricky, but other than that, they should be sort of straightforward. Okay.